Hello, geometry students. Mrs. Myers here. We are on day 2 of coordinate geometry proofs. Today we are going to be looking at the conditions for a rhombus as well as the conditions for a square. So we previously spoke about how to prove that you have a parallelogram. Okay, there are 3 different methods to do that. Now we're going to take the special type of parallelogram called a rhombus. We're going to talk about 2 different ways that we could prove that you actually have a parallelogram becoming a rhombus. Okay, so this is important though that we're already starting off with the fact that it's parallelogram. If you did not know it was a parallelogram, you'd have to go back and reprove that first. Okay, so there are based on the definition of a rhombus and the properties of a rhombus, there are actually 2 different ways to get that the figure to be referred to as a rhombus. If 2 adjacent sides are congruent, then the parallelogram is a rhombus. This is one way to do it. And if the diagonals of a parallelogram are perpendicular, then the parallelogram is a rhombus. That's the other way to do it. So this is an or. Okay, there's 2 different ways to do this. So example 3, having 2 methods. Each one of these is for one of the methods. Okay, but we're going to take the same set of coordinates. Okay, and I'm going to take the time to just make a quick little sketch over here so we can see it. So A is -3, 2. Okay, right there. And we're going to put the coordinates right next to point A. Okay, B is -2, 6. Okay, C is 2, 7. I actually need to make that go a little higher here. And finally, D is 1, 3. Okay, so let's take a look at this figure here. All right, so I know I didn't do the greatest job sketching it, okay, but that's the idea there. We want to prove, knowing that this is already a parallelogram, so it's very important, okay? The fact that we already have it means we don't have to prove it. If it just said quadrilateral, we need to prove it's a parallelogram first. Anyway, so we already know this is a parallelogram. Now we want to know if it's a special type of parallelogram called a rhombus. So can we prove that 2 adjacent sides are congruent? Okay, if we can do that, then it is a rhombus. So let's start by using the distance formula, because the distance formula is what would prove congruency. We have any 2 sides that we can pick that are consecutive adjacent, okay, one right after the other. So for example, side AB. All right, and remember the distance formula. Okay, let me put it at the top of the paper here. Okay, distance formula is x2 minus x1 quantity squared plus y2 minus y1 quantity squared, all underneath the square root. Okay, so that's the distance formula. We're going to use that here. So we just basically take the 2 points here, A and B. Okay, one of them is x1, y1, one of them is x2, y2. We're going to subtract the x coordinates and square it, subtract the y coordinates and square it. So for example, I could go -3 minus -2, and then I would do 2 minus 6. Okay. Add the opposite for minus the negative, so now we're looking at -3 plus 2, so that's -1 squared. 2 minus 6 is -4. Notice the use of the parentheses there. -1 squared is 1, -4 squared is 16, add them to be 17, so square root of 17, that's the length of side AB. Now, I have 2 choices of sides that I could use to prove that I have a rhombus here, because it's any side that is going to be right after this side, like consecutive to it, okay? So AB to BC or AB to AD, doesn't matter which one, so let me just pick BC here. Okay, so get myself all set up to use the distance formula, and I'm going to, for example, go 2 minus -2 for x2 minus x1, and in that case I'm going to go 7 minus 6 for y2 minus y1. 2 minus -2 is 4, because you're going to add the opposite there. 7 minus 6 is 1. All right, 4 squared, 16, 1 squared, 1, add them together, square root of 17. So notice that they are exactly the same length. So remember what we need to do, okay? We need to write our statement and reason. So we are saying that AB is congruent to BC. Why? Because we have the same slopes, okay? So remember how we do that. right? You always take what you've learned from your use of your coordinate geometry formula, you write a statement, you state the reason why that is true. Okay, so we use the distance formula to prove that two consecutive sides, okay, two adjacent sides were congruent. So now what do we know? Okay, given that this has already been proven to be a parallelogram, now we know that parallelogram ABCD is a rhombus because we have two adjacent sides congruent, okay? But let's do the other way, okay? The other way is if we look at the diagonals, remember the diagonals are connecting those opposite vertices, okay? Are those diagonals perpendicular? Because if the diagonals are perpendicular, then this parallelogram would have to be a rhombus. So that requires the use of the slope formula. Slope formula is y2 minus y1 over x2 minus x1. All right, so I'm going to come here and I'm going to find the slope of the diagonals. So I go slope of BD, okay, that's one diagonal. And then I'm going to find the slope of AC, okay, that's another diagonal. So y2 minus y1. So for example, with BD, I'm going to go 6 minus 3 for y2 minus y1. And then I'll go negative 2 minus 1 for x2 minus x1. So 6 minus 3 is 3, negative 2 minus 1 is negative 3, and then this reduces down to negative 1 over 1. I just moved the negative into the numerator. It's a bit more common to do that. All right, slope of AC. So now look at these 2 points AC. I'm going to go 7 minus 2 for the subtraction of the y's, 2 minus negative 3 for the subtraction of the x's. So 7 minus 2 is 5, 2 minus negative 3 is positive 5, and that reduces down to 1 over 1. Now, it's not as obvious with the reciprocal part here because the numerator and denominator are the same, but we could still call those reciprocals. And then they have to be negations of each other as well. Okay, so negative 1 over 1, and this is positive 1 over 1, so we would call these negative reciprocal slopes, and that's what's needed for perpendicularity. So I go BD is perpendicular to AC, and I go negative reciprocal slopes. Okay, not to be confused by same slopes is what proves that lines are parallel. Okay, we're looking for perpendicular here, so we need negative reciprocal slopes. And then we would say, okay, because the diagonals of the parallelogram, again, remember, we already had this started out to be a parallelogram. Okay, so we would say that parallelogram ABCD is a rhombus, okay, because right here, the diagonals are perpendicular, right? Because the diagonals are perpendicular. All right, so that was the second way that we could have proven this, okay? One or the other. All right, let's move on to proving the square. Okay, so hopefully you, already printed everything out, and you can just continue with the next handout, or you're going to be writing this on loose leaf paper. Okay, so now to conditions for a square. So if you remember your flow chart that we did much earlier in the year, okay, a square is really a special type of rhombus and rectangle together, okay? It's a specialized rhombus and a specialized rectangle. So we've got two different ways to do this, okay? We could either prove that it is a rhombus by having consecutive sides congruent, and prove that it's a rectangle by having consecutive sides perpendicular, which means it's form a right angle. So we're doing something to prove that it's a rhombus and something to prove that it's a rectangle at the same time, so it must be a square. Or here's the other way: if the diagonals are congruent, that makes it a rectangle, and then if the diagonals are perpendicular, that makes it a rhombus. So again, we'd be doing something for each of these. All right, we'd be using something that proves that it's a rectangle, something that proves that it's a rhombus, and together that would make it a square. All right, so let's look at the vertices of the figure here and see what this gets us. All right, so we got 1, 5. Okay, so that would be E. F is 6, 5. Okay, G is 6, 10. And then H is 1, 10. All right, so let's write in those coordinates here. I always think it's easier to have them staring you right in the face next to the vertices. Okay, so we want to prove that this is a square. All right, so first thing we're going to do is use the distance and the slope formula with the sides. So that's this first method right here. Then we're going to use the distance and slope formula with the diagonals. Okay, so then that's that other one right there. Okay, so when we're talking about using the distance and slope formula with sides, it needs to be consecutive sides. Okay, so basically one side right after the other. Okay, so those are like adjacent sides. So for example, we could use side EH. Okay, and what we want to do is we want to find the length of that, which means we use the distance formula. Okay, and then we would have a side that's adjacent to consecutive to EH, and that would be HG. Okay, so let's see what that looks like. So for EH, for example, I would go 1 minus 1 quantity squared, and then I would go 10 minus 5 quantity squared. Okay, so 1 minus 1 is 0, 10 minus 5 is 5. Okay, 0 squared is 0, 5 squared is 25. Add that together, square root of 25. Now we could call that 5, but that's not really necessary. All right, HG, so x2 minus x1, for example, would go 6 minus 1. y2 minus y1, I'd go like 10 minus 10. All right, so then this is 5 squared plus 0 squared. All right, 25 plus 0 is 25, so we get the square root of 25. So what we see here is the same exact lengths for these two segments. So I will write my statement, which is that EH, okay, is congruent to HG, okay? And I write the reason, okay? The reason is because I have the same lengths. That's how I know that they're congruent, okay? Now I'm also gonna take that same pair of adjacent sides that I just proved were congruent, and I'm gonna prove that there's a right angle forming between them, okay? So I would need to use the slope for that. That's perpendicularity. So I'm going to do slope of HE, okay? And then I'm also going to do the slope of side HG. All right, so remember that's your y2 minus y1 over x2 minus x1. So I've got 10 minus 5, and I've got 1 minus 1. All right, so this is 5 over 0, and over here, slope of HG. So now I've got 10 minus 10 for y2 minus y1 and 6 minus 1. Okay, so that is 0 over 5. Now, the thing with this, a little bit different, okay, than what we typically would see with two slopes that we would want to prove perpendicular, because this is automatically a value of 0, and then this is what we call undefined. So it's a little bit different to prove that these are perpendicular here by using the slopes, but in a way, the slopes are kind of guiding us to prove something. So because we got a slope that's undefined, that automatically means that we have a vertical line segment. And because we got a slope of 0, that automatically means that we have a horizontal line segment. Well, what do we know about a vertical and a horizontal line segment? Of course, we know that they are perpendicular, okay? So HE is perpendicular to HG, okay? Vertical is always perpendicular to horizontal. I mean, for any other case, we'd say negative reciprocal slopes to prove perpendicularity, but again, can't really use that here because we got these two very interesting types of slopes. But anyway, nonetheless, we did prove that they're perpendicular because one segment we proved was vertical by its slope, the other segment we proved is horizontal by its slope. So now we can say that figure EFGH is a square because, and look what we proved, right? We proved two consecutive sides are congruent and perpendicular. See, we proved that right there. Two consecutive sides are congruent and perpendicular. All right, so that was one method. Now we can do the other one. So the other method calls for us to use this distance and slope formulas with the diagonals. And the reason why it calls for it to be done with the diagonals is because, look at method number 2, if the diagonals of the parallelogram are both congruent and perpendicular, okay, then you've proven that it is a rectangle and a rhombus at the same time. Remember, congruent diagonals means it's a rectangle. Perpendicular diagonals means it's a rhombus, and if you do both of those at the same time, well then a square is what you have proven. So the diagonals are right here, those two segments. So let's start by finding the length of segment HF. Okay, that's one of the diagonals, and then we'll find the length of segment EG, that is the other diagonal, and let's see what those lengths are. Again, we want to prove that they are congruent, so we're hoping that these lengths are the same. So let's take HF first, and we've got 6 minus 1 for y2 minus y1, and we've got 5 minus 10 for x2 minus x1 and y2 minus y1. So 6 minus 1 is 5. Make sure you're going to square that. 5 minus 10 is negative 5. You're going to square that. Each of those values squared is positive 25. Add them together, and that's square root of 50. So we're hoping that EG's distance is square root of 50 as well, because then they would be the same lengths and they'd be congruent segments. So let's see. Okay, so EG, 6 minus 1, there's your y2 minus y1, 10 minus 5, okay, there's your x2 minus x1 and y2 minus y1. So 6 minus 1 is 5 squared, 10 minus 5 is 5 squared. Each of those squares to be 25, adds to be square root of 50, and indeed they're the same. So we write our statement, HF, segment HF is congruent to segment HG. Remember, when you're finding the lengths of them, you don't put the bar over them, but when you're stating them as congruent segments, you do put the bar over them. And why do we know that they're congruent segments? Is because we have the same lengths. All right, so now what we want to do is prove that those diagonals that we know are congruent, are they also perpendicular? Okay, so we're going to find the slope of segment HF, and we're going to find the slope of segment EG. So let's see what we get. All right, so y2 minus y1 over x2 minus x1, so HF first. For example, we've got 10 minus 5, okay, for y2 minus y1, and then we got 1 minus 6. So 10 minus 5 is 5, 1 minus 6 is negative 5. That reduces down to negative 1 over 1. Slope of EG, so 10 minus 5 is y2 minus y1, 6 minus 1, x2 minus x1, so that's 5 over 5, and that reduces down to 1 over 1. So again, not super easy to see the reciprocal thing, because the change in y over change in x is both 1, but they are indeed still reciprocals anyway. And then we can see negative and positive slope. So we are going to say HF is perpendicular to EG. Okay, these two diagonals are perpendicular because they have negative reciprocal slopes. And now that we've done that, we can say that EFGH is a square, okay, because, okay, why? So you can come back up here and look at this reason. It says because the diagonals are congruent and perpendicular. All right, so that is now sufficient. You have proven that you have a square. These are two different methods, okay? You wouldn't have to prove both. You would just prove one or the other. All right, hope that you're catching on to these coordinate geometry proofs. We do have one more day of this with respect to proving trapezoids, okay, using these formulas. And then we have really a fourth day that we're tying into this, which is going to be to find unknown vertices to create one of these special types of quadrilaterals. All right, so next week we'll still be working with these formulas. Let me know if you're not catching on to this, and I will do what I can to help you. All right, bye.